actually chapter 3. Chapter 2 is a big chapter, but that is a lot of information. So from chapter 4, we talk about is the Kepler's equations and Kepler's. Okay, so first one, let me introduce, give you a very brief the overview of the contents we're going to learn in chapter 4. And this one, in chapter 4, we're going to do a little bit more practical techniques to learn the practical way to predict the location of the satellites on his orbit. Okay, and this one will bring our learning to a big step ahead. And with this technique, I think you are pretty much at the end of this learning of this chapter. I think you will be pretty much outstanding from most of the majority of the public people. Okay, then you can pretty much communicate with NASA or professional agencies with very good and in-depth knowledge about whatever they in this field. Okay, so let me define what is the Kepler's problem. So here is our orbit, and say here right now from this moment onward, our focus will be on the objects surrounding the Earth. So here I just take satellites as the example, and this one satellites can be also I would say ballistic missile is one special case of the satellites. Okay, so for example, here is the center of the Earth, and this is the Earth. And why I said the ballistic missile is a special case of the satellites, and this is a case if this is the Earth, and this is the center of the Earth. If here you launch whatever the object, then you launch it at the launching locations, and you have R, and the people, or say the agencies, will be able to detect your launching velocity, and you have V. Okay, so depends on R and V, you can right away in a few seconds, and you can pretty much from radar's information, you can pretty much they can predict the trajectory, the orbit of these objects. If that orbit will be looking like this, then watch out and go to find the ground cavity and then hide yourself. So if that is something like this, if the orbit will be looking like this one, see that one actually intersecting with Earth. Basically, this is we define as the missile, ballistic missile, right? Got it? And that one go out to the space, and then they're going to hit you in certain locations. Okay, so that one, actually, this is a special case of the, I would say, the satellite, right? Okay, the same thing. But here, in this chapter, it's not our focus here, so I'm kind of decide chatting. So for this case, this is our focus, and this is our Earth. And say this is the perigee, and assuming we have a satellite moving in the orbit in say counterclockwise direction, and here we can measure is the mu. Mu is the true anomaly, and true anomaly, that is the angle measured from the reference, which is the perigee axis to there. Now we want to impose is this, and so far we have learned is purely geometric. That means we know the size, we know the shape, and we know the whatever these things, but we don't simply haven't embedded any time information yet. So which means right now, say we want to know when the satellite will be here, when the satellite will be here. So for example, say starting from here, I would say this is T0. And to this moment, say that will take about T, certain amount of the T to traveling from here to here. We want to know how much time spent from here to here. If we have this technique, then we can predict when the satellite will appear at where, right? So right now in these chapters, we are going to begin to kick into the information one additional domain or one additional dimension, which is time. So that is the Kepler's problem. So in this way, the Kepler problem have two aspects. The easy problem of the Kepler's in the Kepler is this. We are given the true anomaly and we find time. Okay, so again, I define the T0 is a time, the reference time at the period, how to say? So say if the satellite is here and that is the time moment. So actually here is the delta T is from here. Okay, so that is delta T. Okay, so I would say find delta T. And the heart, the problems is we given delta T, we're going to find the true anomaly. Okay, so and I'm going to show you why how did people define it as easy and hard. So basically, the second problem will be involving is the predictions of the such locations, because say for the right now the United States do have the kind of the military activities in the Middle East. So their opponents on their side, they must be survived and learning this the techniques because always they the spy satellites monitor their activities. But those kind of spy the satellite they've been through, they have their own patterns, and the opponents they have those parameters, so they want to know, they can learn say when we have to go to hide before being detected by satellite. Okay, so for this case, this is about the prediction of the satellite location. That means that given the certain amount, say 20 minutes, I want to know after 20 minutes where is the location of that satellite, and that satellite will have the side view, they call the line of view, and to certain place on the Earth. Okay, so that is the kind of the information here. So given this one, this is the overall the contents of these chapters. And we will start with this one. We will start with the easy problem, and by solving the easy problem, we can also learn what is the definition in exactly about the Kepler's problems. Okay, and the hard problem in terms of the easy and hard is in terms of the calculation rigors. We call the computational loading, the computational load. And easy problem is only involve one very simple line, and then we punch in calculate so we can get the answer right away in a few minutes. The hard problem is the problem like this. The hard problem is something like this. Say 3 equal to, let me make up one. S3 plus 2x plus, say, sine x, and solve for x. Okay, so hard problem is something like this one. So for certain, we can be lucky and we can find the x, but most of the time, from here, ES301, you know, for this kind of problem, we have to do the numerical way. And in ES301, we have introduced quite a bit techniques. For example, bisectional method, or the Newton's method, which means the shooting method. Okay, and hopefully this can remind you what you learned before. And this one basically definitely we have to go to numerical. So that means here in quite a bit of our lecture contents will be borrow the concept, the methods from before, and then in particular apply to our problems. Okay, so that is the reason last Friday I sent you the email reminding you from this point onward we will involve quite a bit programming, and that is the reason here. And again, in the futures, all of my related the lecture materials regarding the programming will be given based upon MATLAB. So I really encourage you to use the MATLAB, and in this way you can right away adapt my information. Or otherwise, I think the people, if you like, and I've seen people before using Excel, and they've been using Expert very good in a very good way. So that's okay. And for the easy problems, and that's something like this, we are given x and calculate the value of x3 plus 2x plus sine x. So you see this one is easy. Okay, so that is the different thing. So basically the hard problem is to kind of root finding questions. And this one is simply the direct calculations. Okay, so that is the overview.